Lecture 9 is Elimination. This is the second half of Chapter 6. Remember that when we started Chapter 6, I told you that we were beginning to delve into this universe of reactions that were classes of reactions. And last lecture we did substitution, SN1 and SN2. Today we're going to do the other two reactions that we're going to call E1 and E2, or elimination first order and elimination second order. Elimination reactions involve creating a pi bond. So we're going to be using reactions that generate a double bond between the carbon by adding a pi bond in addition to a sigma bond. Before we jump into elimination first, though, I want to make somewhat of an addendum to last lecture about using alcohols or OH groups on a carbon as nucleophiles. So we have two options here. Here I'm showing an alcohol, and you can see that I'm doing a substitution reaction where I'm taking electrons from the oxygen on the alcohol. Those electrons are attacking a carbon with a bromine leaving group, and as I'm forming a bond to the carbon, the leaving group is leaving. So since I'm showing this in one step, meaning both arrows are occurring simultaneously, that means this is an SN2 reaction, second order. The two species that are involved in the reaction, the rate limiting step, are the alcohol nucleophile and the substrate with the leaving group. Notice that with the alcohol, the oxygen is neutral. We have 2 lone pairs, so it's neutral instead of 3 lone pairs with a negative charge. So because that hydrogen is on that oxygen, after the displacement, that hydrogen is still on that oxygen. We've displaced the bromine, but we don't have a neutral molecule. The oxygen now has 3 bonds and only 1 lone pair. Remember that we used one of the lone pairs to make an additional bond. So that's where we get 3 bonds and we only have 1 lone pair left. Therefore, we have a positive charge. We need one more step to complete this reaction. To end up with a neutral oxygen and a neutral molecule that's purely organic, we need to remove this hydrogen. So the second step in this reaction involves the bromide, which was our leaving group. Remember, we displaced bromide in the first step. Will come back and donate its electrons and grab that hydrogen. So it's going to use its electrons to make a bond to that hydrogen. We're giving hydrogen a second bond now, which it's not allowed to have. So hydrogen needs to release itself from the oxygen, and it does so by letting go of the electrons in the HO bond, putting those electrons back onto the oxygen. So now we have neutral oxygen. Our byproduct then would be HBr. That's what we get if we use an alcohol as a nucleophile. There's another option, is we can take that alcohol and react it with sodium hydride, NaH. That's Na plus, H minus. Hydride, H minus, is a pretty strong base. It's a pretty nasty base. It turns out that hydride is a poor nucleophile, but it's a pretty good base. And what it will do, the hydride will grab the H off of the alcohol and generate O minus, kind of the same mechanism that we showed here. Hydride would grab the H, put the electrons onto oxygen so that we have O minus and then Na plus. That also generates H2, which is a gas, of course, and that bubbles away. The fact that one of our products that we form bubbles out means that the equilibrium of this reaction is always being driven towards the products because we're constantly losing product. That also gives us a very strong nucleophile. So O minus is a better nucleophile than OH. Remember, we said that a base is always a better nucleophile than the conjugate acid. So once we've used NaH, sodium hydride, to remove that H from our alcohol, we now have an alkoxide, which is a better nucleophile. If that oxygen donates its lone pair of electrons to the carbon, and the bromine leaves as a result. Again, still an SN2 reaction. And now we end up with a neutral oxygen. We start with a negative oxygen, give it an additional bond to make it neutral. Or we start with a neutral oxygen, give an additional bond, it'll be positive. We have one more step that the mechanism needs to go through in order to get to our products. In this case, the byproduct is sodium bromide. We have sodium plus floating around here, was originally paired with hydrogen. Hydrogen bubbles away. Na plus ends up being paired with O minus. O minus ends up getting paired with carbon. So now we have a bromide and Na plus. We have an ionic salt, a byproduct here. That's inorganic. So these two pathways, the top pathway is a slower, gentler reaction. We have a weaker nucleophile. And so the reaction will proceed slower with less exothermic character. We also end up with HBr, which is covalent. We do not get ionic byproducts in this top pathway. The bottom pathway is a much faster reaction. We introduce a very reactive reagent to generate a stronger nucleophile, but as a result of that, we also end up with an inorganic byproduct that we need to separate out. So we have a faster, messier reaction in the bottom pathway, or a slower, gentler reaction in the top pathway. But in both cases, we still get the same organic byproduct. The cyclohexane ring attached to an O, attached to another cyclohexane ring. So just be aware that you can use alcohols as nucleophiles. You don't need to use the alkoxide as a nucleophile. When you use an alkoxide, you get to your product faster, more exothermic, more driven by equilibrium, but you have messier results. Or you can have a slower reaction that ends up with fewer byproducts. Okay, so let's look at where we are before we jump into elimination. We talked about orbitals. We learned about hybridization and molecular orbital theory, and how orbitals give us a sense of where the electron density is, or where the highest energy orbitals are and where the lowest energy orbitals are. And we kind of saw how that gives rise to molecular shape, molecular structure, and bonding. We looked at alkanes and conformations of alkanes. We learned nomenclature of alkanes. We then took those alkanes and learned free radical chain reactions, where we could transform alkanes into alkyl halides, put a halogen onto a carbon framework. Last time, we took those alkyl halides and we substituted them, either substituting methyl primary and secondary alkyl halides with a nucleophile of choice in an SN2 substitution, or taking secondary and tertiary alkyl halides, substituting them with a nucleophile of our choice in a first order substitution. I want to point out that depending on the nucleophile that you use, you can determine what your functional group in your product is going to be. If you substitute an alkyl halide with alkoxide, OR minus, you get ethers. If you substitute your alkyl halide with a hydroxide, you get alcohols as your product. If you substitute alkyl halides with NR2 minus, amides, you get amines as your product. If you substitute it with SH minus, you get thiols as your product. If you substitute it with SR minus, you get thioethers as your product. So just by taking an alkane, adding a halide to it to make an alkyl halide, and then substituting that, we now have kind of a pathway or a route to give us access to many of these other functional groups. Notice back here, when we used an alkoxide or an alcohol, when we use an alkoxide or an alcohol as our nucleophile, our product that results from substituting an alkyl halide was an ether. This is an ether, an ROR functional group. So now we're going to add two more pathways that are going to allow us to create a double bond by removing a hydrogen and a leaving group simultaneously. We can do that in a second order mechanism, which we're going to call E2, or a first order mechanism, which we're going to call E1. So here's E2. We started with SN2 last time. We looked at the second order mechanism last time. So let's start with the second order mechanism this time. We're going to call a second order elimination reaction E2. And here's the big picture. We have some substrate that, let me show you, involves a leaving group, in this case a bromine, adjacent to a hydrogen. And what I mean is that we have a carbon bearing a bromine, or a carbon bearing a leaving group, adjacent to a carbon bearing a hydrogen. And you'll notice that the big picture here is that we use a strong base, which is a weak nucleophile. We talked a little bit about weak nucleophiles in the case of SN1. A weak nucleophile could be a strong base if that base is very, very bulky. A bulky base makes a poor nucleophile. And that's what we need in this case. The base grabs one of these hydrogens, one of these adjacent hydrogens, and you'll notice that the product, we have lost our bromine, we've lost our leaving group, we've also lost one of our hydrogens, we've only got one hydrogen left. We make that double bond between the two carbons. The carbon that bared the bromine and the carbon bared the hydrogen now share a double bond, and we can get Z or E geometries. Notice that this is the Z because the larger group on the left is the methyl, and the largest group on the right is the ethyl, and those two groups are on the same side of that double bond, the same face of that double bond. This is E because here the methyl is the largest group on the left, the ethyl is the largest group on the right, and they're on the opposite face of that double bond. So these two groups are the groups of interest. The hydrogen on one carbon and the leaving group, or the bromine, on the adjacent carbon. Let's ask ourselves a couple questions. First few questions that are probably jumping out at you, or hopefully are jumping out at you at this point, is what does the base do? What role does the base play in this reaction? Another question that you might be wondering, why must the base be a weak nucleophile? How are we forming the double bond? What is it, the mechanism that gets us from our starting material to the product, and how is the double bond formed? We could ask ourselves, why do we get both E and Z geometries? Or are there some conditions when we only get the Z? Or are there some conditions when we only get the E? And how can we control that? Or can we control it at all? Maybe there's sometimes when we have to get both. And what does the rate equation look like? We looked at kinetics before, and we saw that we looked at the kinetic rate equation for SN2. You might be wondering, does the rate equation for SN2 look similar to the rate equation for E2, since they are both second order reactions? So here's the mechanism, and if you were concluding or assuming or guessing that E2 is a lot like SN2 because they are both second order, you are right. The mechanism for this transformation from our starting material to our products involve only one step. This mechanism, this reaction occurs in one concerted step, and it looks a lot like it did for SN2, where the rate of the reaction is equal to some rate constant times the concentration of our substrate times the concentration of our base. We're going to be using something that's going to act as a base instead of something that acts as a nucleophile. And here's what it looks like. Here's our base. I've chosen butoxide, tertiary butoxide, because that's a big, bulky base. That's a poor nucleophile. It's too bulky to access the antibonding orbital of this leaving group by itself. So it's a very poor nucleophile, but it's a good base because it still has high electron density, high charge density, and can easily remove a hydrogen that's on the kind of outskirts of this molecule. So the base is going to donate its electrons into the antibonding orbital of this hydrogen. The electrons that were keeping the hydrogen bound to that carbon are going to be liberated. Remember two things here. Hydrogen can only make one bond. So if we are going to create a new bond to the oxygen, that hydrogen has to let go of the bonding electrons to the carbon. Additionally, by populating the antibonding orbital to the hydrogen, you displace or you break or you weaken the bonding electrons to the carbon. The corresponding bonding orbital is weakened by populating the antibonding orbital. So when those electrons are liberated, they are then immediately donated into an antibonding orbital involving the bromine, involving the carbon bromide bond. And in doing so, we are going to make a pi bond, and that corresponding bonding orbital is broken. So the bromine leaves. That gives us the carbon-carbon pi bond from these electrons, and the bromine is liberated. There is one major requirement for the E2 mechanism to occur, and that is that the hydrogen that gets removed by the base and the leaving group that leaves, in this case the bromide, must be what we call anti-coplanar to one another. That basically means that they have to be anti to one another in the Newman projection and in the same plane. So 180 degrees from one another. In the Newman projection, it looks like this. Here's our front carbon. That you see is the carbon with the two hydrogens and the methyl. That's this carbon right here. Here's our back carbon as methyl, ethyl, and bromide. So our back carbon has methyl, ethyl, and bromide. And what we see here is that the hydrogen that gets removed by the base is anti at 180 degrees from the leaving group, and they are in the same plane. They are completely flat. If we were to imagine slicing this molecule right in half across a plane like a knife, that hydrogen and the bromine would get sliced by that knife. That is the single requirement for E2. So the way that I drew this is actually very specific. Notice that the hydrogen here is pointing kind of up and to the left, and the bromine here is pointing kind of down and to the right. That makes them anti and coplanar. This hydrogen is not anti-coplanar to that bromine. It's not pointing in the anti-opposite direction from that bromine. So specifically here, as drawn, it's this hydrogen that gets removed, not this hydrogen. So why does that happen? Why is that the requirement? What's causing this bromine to leave specifically as a result of this hydrogen getting removed? Well, let's look at the orbitals. Almost always, when there is a specific spatial requirement involved, that the bromine be spatially related to the hydrogen that gets removed, that must involve orbitals. The location, the position in space, the three-dimensional relationship between two different orbitals almost always is what is responsible for these specific products being formed. So let's look at where the orbitals are. Here's our Newman projection. Notice that the hydrogen on the front carbon is anti-coplanar, anti at 180, and in the same plane, you can slice both of them with a knife. If you slice right through the middle of this molecule, the hydrogen and the leaving group, in this case, they're just using X as a halogen, shorthand for a halogen to specify a leaving group. They're at 180. And if we look at the arrangement of this molecule in 3D and think about where the particular orbitals are, it would look like this. Here's our carbon leaving group bond, and here's the anti-bonding orbital that corresponds to that bond. Here's our carbon-hydrogen bond, and here's the base that's going to grab that hydrogen. Notice very specifically here that the electron pair right here that gets liberated when the base grabs the hydrogen is already aligned. It's in the same plane with the anti-bonding orbital of the carbon leaving group bond. So what happens is when the base grabs the hydrogen, these electrons are lined up with this antibonding orbital, and they will feed into that antibonding orbital rather than the base grabbing the hydrogens and the lone pair sitting on this carbon. Rather than that happening, the lone pair will feed into that antibonding orbital, and we end up making a pi bond. As we feed into that antibonding orbital and making a pi bond, the feeding into that antibonding orbital breaks this bond, breaks the corresponding bond, the bonding orbital corresponding to the antibonding orbital, and that causes the leaving group to leave and take its electrons with it. That, of course, requires that these groups, the H on the carbon and the leaving group on that carbon, be staggered and be anticoplanar, that this group here and this arrangement here be staggered, and therefore these groups be anticoplanar. So the hydrogen carbon bonding electrons that are liberated must be aligned with the carbon leaving group antibonding orbital so that they can populate that antibonding orbital, and as a result of that, displace the leaving group. Notice that we have concomitant rehybridization to sp2. That means that as this process is happening, this carbon is losing an entire group, and this carbon is losing an entire group. So we are going from having 3 groups around this carbon to 2, and 3 groups around this carbon to 2. And in place of those missing groups, we make a new pi bond. That means that we're going from being sp3 over here and sp3 over here to sp2 in both cases. So our geometry changes. These groups, the remaining groups, end up being planar. And these groups end up being planar. And we've got 2 bonds, a sigma bond here, and the pi bond shown in these kind of balloon pictures are our 2 bonds, and our leaving group has left. Now let's look at why we get both the E and the Z products as a result of this. Sometimes you will see we will only get the Z, and sometimes you will see we will only get the E. But in this specific case, we get both. The reason why that is that there are 2 hydrogens on our front carbon, that hydrogen there, and either of these carbons could at some point be anti to this bromine. Because of that, I'm going to show you we can get the Z and the E products. Let's look here. This hydrogen, as drawn, is currently anticoplanar to our leaving group. And when this hydrogen is anticoplanar to the bromine, these methyls, you notice, are apart from one another. Or you can see it as this methyl and this ethyl are near each other. So in this particular configuration, where this hydrogen and this bromine are anti to each other, the methyls are apart. And so when this pi bond forms, when this process happens, when the mechanism proceeds, the methyls get locked on the opposite face of one another. See that? They are apart from each other in the Newman projection, and they are apart from each other when the bond is formed, when that pi bond is formed. When that pi bond is formed, this methyl here and this ethyl here are the larger groups. So this methyl being here and this ethyl being here, and those largest groups being on the same face of the alkene, the same face of that pi bond, means that this is the Z. But notice that if we rotate these groups relative to one another, such that this hydrogen ends up here, so that this hydrogen is anti to this bromine. So what I'm going to do, I'm going to take our front carbon, the hydrogen and the methyl, and I'm going to rotate it. I'm going to rotate the methyl group so that it's there, and that hydrogen so that it's there, and that hydrogen so that it's there. I'm going to rotate that entire front carbon and the 3 groups that are attached to it so that we end up with this Newman projection. Look what happens now. Now, this hydrogen is there. So that hydrogen is now anti to that bromine. Now, when the base grabs that hydrogen and these electrons fall in, and that forces off the bromine. The leaving group leaves. Notice that the methyl groups are right next to each other, so that when that pi bond is formed, these methyl groups are right next to each other. Now, in this alkene, in this pi bond, and this molecule in our product, this ethyl group is the largest group on this carbon, and this methyl group is the largest group on this carbon. That means that our largest groups are on the opposite faces. They are apart from each other. So we end up with the E. I want to just clarify here the fact that these methyls are farther away from one another is not what makes this the Z. And the fact that these methyls are close to one another is not what makes it the E. I'm just highlighting these similar groups. If I take this and do that, and take this and do that, and take this and do that, and take this and do that. Now I'm highlighting which groups give us the Z, and I'm highlighting which groups give us the E designation. We'll do a couple more examples involving this strategy later. Let's turn to chair conformations for a moment. Here's a line angle structure where we have a hydrogen on a carbon adjacent to a bromine on a carbon. And as such, we have a substrate that is susceptible to an elimination reaction. If you look at the dash and wedge for each of these, you see that bromine is dashed, hydrogen is wedged, which practically means that they are anticoplanar to one another. One of them is pointing straight up at us, the other one is pointing straight down at us. But there are some things to consider. If we draw this line angle structure as a chair, we could draw it like this. Here's our chair. We could put our methyl up, axial, our bromine down, equatorial. Then we could put our hydrogen up, equatorial, and our ethyl down, axial. You notice that in this conformation, the hydrogen and the bromine that need to be anticoplanar in order for this mechanism to proceed are not anticoplanar to one another. They are both equatorial, where one of them is kind of pointing down and away, and the other one's kind of pointing up and away. But remember that we can do chair flips. And if we flip this chair, remember that any group that was equatorial ends up flipping to be axial. So if we flip that, here's our bromine up, axial, and here's our hydrogen down, axial. Now we have a configuration where the two groups are aligned properly. The antibonding orbital of the carbon-bromine bond is underneath the ring, kind of right around here, and that is exactly aligned with where the electrons on the carbon-hydrogen bond are. And that's, remember, the reason why we need an anticoplanar arrangement is so that because the electrons that get liberated can line up with the leaving group's antibonding orbital. So this molecule can undergo E2 elimination. Remember that there's an equilibrium between these two chairs. And in the event that one of these chairs is more favored than the other, that may or may not help the elimination reaction. For example, this conformation is required for the reaction to take place. But if for some reason the other chair conformation was more favored, then we would have a situation where the chair would spend all of its time in one conformation where the reaction can't occur. Now, in this case, it is actually true that the chair on the right is the more favored conformation. That puts the methyl group and the ethyl group equatorial, whereas the other chair only puts the bromine equatorial. So between this equilibrium, we're going to spend more time on the right structure than the left structure. And as a result of that, we're going to have a chair in a conformation that is susceptible to elimination. Here's a different chair. Now notice what I did. I'm going to go back. Notice the methyl and the bromine. Here the bromine is a wedge and the methyl is a dash. Before it was the opposite. The methyl was a wedge and a bromine was a dash. So if we change that one carbon, we change the stereochemistry of that one carbon and leave the stereochemistry of the other carbon the same, look what happens. Again, we can draw the chair and we can say, okay, bromine is a wedge, so it's up. And so the methyl is dashed, it's down. And the hydrogen is a wedge, so it's up. And the ethyl is a dash, so it's down. Notice again that the H and the bromine are not in that anticoplanar arrangement. The antibonding orbital of the carbon-bromine bond, again, is under the ring, whereas the electrons from the carbon-hydrogen bond are above the ring. So those are not aligned. And even when we flip the chair, we still have that problem. Now, the antibonding orbital of the carbon-bromine bond is kind of up here, kind of up into maybe above the ring, above the plane of the ring, and the electrons from the carbon-hydrogen bond are down underneath the ring. So again, they're not lined up. In neither conformation do we get the bromine and its neighboring hydrogen anticoplanar, such that they're both axial. So this molecule will not undergo elimination. It's important to pay attention to the conformational freedoms or limitations in a structure before you evaluate whether you can actually undergo the reaction. Just because you have a leaving group and adjacent hydrogen does not necessarily mean that the reaction will proceed. So here's a problem to work on. We've got a substrate, a 4-carbon chain with a leaving group. Our bromine is our leaving group. And we've got a big bulky base, sodium T-butoxide, NaOTBu. So we've got a situation here, reaction conditions, that should allow for E2 elimination. And I'm telling you that there are 3 elimination products. So you can pause the video if you want. Try to figure out what the 3 elimination products could be for this molecule. Okay, here are 2 of them. Remember, what we need to look for are hydrogens that are on carbons adjacent to the carbon bearing the leaving group. So there are 2 hydrogens on this carbon. And like we saw before, when you have 2 hydrogens adjacent to a leaving group, one of them can be eliminated to give rise to the E, and one of them, or the other one, can be eliminated to give rise to the Z. So there are 2 of our products, each one arising from removing a specific hydrogen adjacent to that bromine. But notice, very importantly, that there is another source of hydrogen. There are 3 hydrogens over here. And because of the geometry of a terminal double bond, you can't have E or Z on a terminal double bond, because on one end you will always have 2 hydrogens. So you can't get E or Z from that. But if we do eliminate from that hydrogen, say our base comes in, grabs the H, the electrons fall in to make the pi bond, and that forces off the leaving group, we get a 3rd product. Think about the relationships between these. These 2, where the double bond is between the 2nd and the 3rd carbon, these are geometric isomers. Same formula, same connectivity, different arrangement in space. This guy down here is a constitutional isomer of the other 2. The atoms are connected differently. Our bonds are in a different place. So those are the 3 products that hopefully you found by analyzing our starting material and thinking about what is required for elimination. But here's a question. Which one is the major product? Which of these three will be formed in preference to the others? And there's no way to know this necessarily just by first principles. This type of information, picking which one of these is the best, is something that comes out of experimental observation. There's nothing inherently theoretical about which one of these would be better or more likely to form. So, as Russian scientist named Alexander Zaitsev figured out a rule for predicting what alkene products will be favored in an elimination reaction. Basically, what he did is he did hundreds and hundreds of elimination reactions on all kinds of different substrates. And by looking at the types of products that resulted, he was able to draw a conclusion. And this is what he said. He said the alkene formed in greatest amount is the one that corresponds to removal of the hydrogen from the adjacent carbon having the fewest hydrogen substituents. So he basically said that if you choose the hydrogen that is on the carbon with the fewest hydrogens, that product will be favored. So if we look at our previous slide, there are 2 hydrogens on this carbon and 3 hydrogens on this carbon, meaning that according to Zaitsev's rule, removal of a hydrogen from the carbon bearing the fewest hydrogens give rise to the most preferred product. So the conclusion then is that these are what we call the Zaitsev product. Both of these products result from following Zaitsev's rule. Now, it was generally the case that the trans geometry, the E geometry, will be the most favored over the Z geometry. It's very close in most cases. E is slightly preferred over Z. There are more extreme cases where E can be very, very favored over Z, and there are even some weird cases where Z can be favored over E. But for the most part, E is very slightly favored over Z. But it's way more favored than the other option, which we call the Hofmann product. So the Zaitsev product is the product that results from following Zaitsev rule. It's the most preferred alkene product in elimination. And we call the non-Zaitsev product the Hofmann product. The reason it's called the Hofmann product is because there is another type of elimination called Hofmann elimination that gives the Hofmann product as the major product. So you might be wondering, why does Zaitsev's product work? Or why does Zaitsev's rule exist? Well, I've shown you this slide before, which is one where we were looking at hydrogenation when we were talking about conjugation, and we were looking at the energies of these double bonds and how much energy it takes, or how much energy is released when you hydrogenate them. And we saw this trend that from unsubstituted to mono to di to tri to tetra, each one correspondingly required less energy to hydrogenate, meaning that the more substituted double bond, the more stable it is. If you look at Zaitsev's rule, these double bonds, the Zaitsev products, are di-substituted. Each double bond here has one substituent on it. This double bond has one there, a methyl group there, and a methyl group there. Di-substituted. This one's also di-substituted, of course, methyl and methyl. But this double bond is only mono-substituted. The only carbon substituent coming off of this Hofmann product, double bond, is this ethyl group, a single substituent. So Zaitsev's rule works because by removing a hydrogen from the carbon with the fewest hydrogens, you will always get the more substituted double bond. One trick for remembering Zaitsev's rule is you can think about safety in numbers. Like a school of fish, the more fish there are, the more safe each fish is. Well, If there are more hydrogens on a carbon, those hydrogens are less likely to get removed by the base. The hydrogens that get removed are the ones that have the fewest hydrogens on that carbon. They are the ones that are susceptible to removal. And that is simply because the result of that gives the better product. I want to show you an example of a reaction where we have to consider Zaitsev's rule as well as whether we will get both E and Z products, or if we will get only the E or the Z and not the one and not the other. So here's an organic substrate, and we have a leaving group. The bromine is our leaving group, and we're using a bulky base. And the question is whether we will get E or Z or both. So let's first consider whether or not we can even do elimination. Remember that we have a requirement that says that we need an adjacent hydrogen to our leaving group. So here's our carbon with our leaving group. That's going to be I'll put it in pink. So we need hydrogens on an adjacent carbon. Now, here's our orange carbon. Here's our green carbon. So we need hydrogens on at least one of those carbons in order for the reaction to work. So our orange carbon has one hydrogen on it. And based on the stereochemistry of that methyl group being a wedged, our orange hydrogen must be going down, going away from us. On our green carbon, hopefully you can tell, we've got two hydrogens. One of them would be wedged, and one of them would be dashed. So we have two adjacent sources of hydrogens next to our leaving group. But remember what Zaitsev's rule says. Zaitsev's rule says that our major product is the one that will result from removing the hydrogen from the carbon bearing the fewest hydrogens, safety in number. So which ones are safe? It's the green ones. Our green ones are more safe to our base than our orange one is. So we know that our reaction should involve our base removing our orange H and those electrons making a pi bond to eliminate our bromine. So the mechanism would look something like this. Our base would come in and grab our hydrogen, the orange one, not the green ones. The electrons fall in between our two carbons to make our pi bond, and subsequently our leaving group leaves. So we do have a situation where we could do E2 elimination, where we have a hydrogen that is adjacent to our bromine. But we also need to make sure that that hydrogen can be anticoplanar to our leaving group. Now, if you just look at the line angle structure, you'll notice that the hydrogen is dashed, meaning it's going down, and the bromine is dashed, which means it's going down, which means that as drawn, these are not anticoplanar to one another. That doesn't mean that they can't ever be anticoplanar to one another. Because remember, we have single bonds here, and we can rotate freely around single bonds. So let's look at our molecule from the perspective of that bond. I want to look down the bond that involves our carbon with our hydrogen and our carbon with our leaving group. So we're looking down that carbon-carbon bond, the orange carbon, pink carbon bond. Now, if we did that, what would we see? Hopefully you can see from this perspective. Now, looking down this bond, the orange carbon, pink carbon bond, what would we see? We've got our methyl group, which is a wedge. So that's coming out of the plane of the board. So that would be, if we're looking from the perspective of that eye, that methyl group would be up and to our right, meaning it's this methyl group right there. That's that methyl group. We've got the hydrogen that's dashed, that's going into the board. So from the perspective of that eye, it would be going up and to our left. That's that hydrogen right there. And then we would see down, we would see an ethyl group right there. And so that's our ethyl group there. So that's what we would see on the front. What would we see on the back carbon? Well, on the back carbon, we have a bromine that's a dash. So it's going into the board. So on our back carbon, we see something that's going down and to our left. So that's this bromine right here. We would see another hydrogen, which I haven't drawn in there. That hydrogen would look like this. It would be wedged right there. So that's kind of going down and to our right. So that's that hydrogen right there. And then we would see an ethyl group coming up. That ethyl group right there, we would see that going up. That's that. So notice where our important atoms are relative to each other. The hydrogen on the front carbon is there, and the bromine on the back carbon is there. Notice that the H and the bromine are not anticoplanar, which means we need to rotate the bond in the direction of these orange arrows. I'm going to keep the back carbon the same, and I'm going to rotate the front carbon around. So as you see in these orange arrows, we're going to take the hydrogen and we're going to rotate it to where the methyl group is. Then we're going to take the methyl group and rotate it to where the ethyl group is. And we take the ethyl group and rotate it to where the hydrogen is. If we do that, this is what we get. You can kind of see the two there. We've now rotated the hydrogen into the position that we need. This hydrogen needs to rotate so that it is anticoplanar to the bromine. So that hydrogen is there and the bromine is still there. So that's what we get down here. We've rotated it into the right position. Now everything is in place. So our base can come in, our big bulky base, grab the adjacent hydrogen. The electrons can fall in between the two carbons and displace the bromine. Now, when this happens, look at where everything is relative to itself. Notice that we have these ethyl groups that are next to each other and the hydrogen and methyl that are next to each other. That's very important because once that pi bond forms and you can't rotate that bond anymore, those groups are locked in that relative position. So here's a trick. Just draw the double bond first. Draw a naked double bond. So there's our double bond with our four positions, our four substituents on it. And look at which groups are next to each other. Like we said, the ethyls are next to each other. They're on different carbons. Don't draw them on the same carbon. Remember, you can see that one ethyl is on the front carbon and one ethyl is on the back carbon. So make sure you don't draw them on the same carbon when you see that they're next to each other. All that means is that they are positioned in the same plane of each other in that double bond. So we could put the two ethyl groups up like that, and the two methyl group, or the methyl and the hydrogen, the other groups, like that. So when we do that, this is what we have. We put the two ethyls together and the methyl and the hydrogen together. If you want to rank these, we could do that. Let's see, how would that look? So on our left carbon, ethyl is the larger group, hydrogen is the smaller group. On our right carbon, ethyl is the larger group, methyl is the smaller group. So again, if we cut this bond right in half and we look at what groups are together, we see the ones are on the same side. So this is the Z double bond. If we were to draw this out, including where the ethyl groups are and the methyl group is, it would look like this. Again, I just converted the ethyls into line angle structure. The ones are together, the twos are together, so this is the Z geometry. So like I say here, the green H is the Zaitsev hydrogen. That's the hydrogen that is reactive in this reaction. And Zaitsev's rule explains kind of the logic behind that. The red hydrogens, even though they are, first of all, greater in quantity and also adjacent to our leaving group, don't actually react. So that is the process that you should always go through when you are evaluating a molecule for elimination. You first want to identify where the adjacent hydrogens are. Then you want to choose which hydrogens would follow Zaitsev's rule. You want to view the molecule as a Newman projection so that you can see whether any of those hydrogens can ever be anticoplanar to our leaving group. If they aren't anticoplanar, you want to try to rotate a single bond around so that they are anticoplanar. Then you proceed with the reaction, locking the remaining groups in their relative position. Then when you draw the molecule out, keeping those groups in that relative position, you can rank them based on stereochemical priority and determine whether the ones are together, such that it's a Z, or whether the ones are apart, such that it's an E. We can do more of these in workshop if you need more help. Let's go back briefly to our big picture and mechanism slide, because I want to highlight some similarities and differences between E2 and SN2. They are both second order reactions, which of course means that they occur in one concerted step where the reactant attacks and the leaving group leaves in the same sequence, not in separate sequences. But you probably recall that in SN2, we were only able to do the reaction if our leaving group was methyl substituted, primary substituted, and sometimes secondary substituted, depending on the strength of the nucleophile. E2 doesn't quite have those same requirements. If you look at our example here, our leaving group is tertiary in this case. You could never do SN2 on this leaving group. It would never work. Now, we are using a strong base, which is ideally a weak nucleophile, in order to ensure against that. In the event that this was a primary leaving group, let's say, then we would be more susceptible to SN2 if our base was too nucleophilic. So there can be a bit of crossover where if your base is a good base, but also a good nucleophile, and your leaving group is primary, and there is an adjacent hydrogen, then you have all the conditions met to do E2 and SN2. The tertiary nature of this example, the reason I chose this example is because we have no risk of any SN2 crossover. E2 can still work even on tertiary leaving groups. Something that is a little bit more important, though, is the accessibility of these hydrogens. You need to be able to access these hydrogens. So most of the time, that won't be a problem. But if the other groups on that carbon are super big and bulky, like if these were T-butyl groups or something very, very large and space filling, then we might not be able to access this hydrogen as much as we might want if our base is as bulky as it should be. So take into account those considerations. There is often some crossover between these reactions, but elimination doesn't have that same strict requirement that SN2 does, where you can't do anything on a tertiary leaving group. So, yes, there is also an E1 mechanism, like I said, and the parallels between E1 and E2 are very similar as the parallels between SN1 and SN2. You might recall that in SN1, the first step of the mechanism was that the leaving group left on its own. Then, and only then, in SN1, did the nucleophile add in to the carbocation that got formed. In elimination 1, E1, it's very similar. So here we show our leaving group leaving first. Before the base even grabs the hydrogen, our leaving group leaves. That again will generate a carbocation. And the second step would be that the base comes in and grabs a hydrogen. The electrons can fall in to make the pi bond, but we don't need to push off the leaving group anymore because it's already gone. We have this big empty p orbital sitting there, already willing and waiting to accept the lone pair as a pi bond from the carbon-hydrogen bond. You'll notice that we also can get E and Z. That doesn't change, but we are now first order. The rate limiting step in this reaction is the one where the leaving group leaves on its own. And that step only involves the substrate. It does not involve the base / nucleophile. So, some things to notice. In E1, the leaving group must be secondary or tertiary because we still have to form a carbocation. So if our leaving group is primary, it's never going to want to leave on its own. That was the same limitation that we had in SN1. That is also true in E1. We need a secondary or a tertiary. So the degree of substitution matters for E1, but not for E2. That's a little bit different than the substitution reactions, where degree of substitution matters for both E1 and E2. So again, we are making carbocations, which means that, again, like in SN1, rearrangements are possible, and we also want to consider resonance structures. The big kicker for E1 is that the hydrogen and the leaving group need not be anticoplanar. Remember that in order for E2 to happen, the electrons from the carbon-hydrogen bond have to feed into that antibonding orbital in order for the bromine to push off. So the lone electrons that get released and the antibonding orbital need to be aligned. But in the case of E1, that leaving group is gone. So there is no antibonding orbital. In place of that antibonding orbital, there's just an unhybridized p orbital that has volume both above the plane of the molecule, above the plane of that sp2 hybridized carbon, and below the plane of that molecule. So it doesn't matter whether the hydrogen's electrons approach from the top face or the bottom face of the carbocation, because both of those faces are accessible. That means that we have fewer stereochemical requirements than E2, but more substitution requirements than E2. Here's that picture. So here's our carbocation, and it's a big empty p orbital. So whether or not the antibonding orbital is on top and the hydrogen is underneath, or whether the antibonding orbital is underneath and the hydrogen is on top, no matter where those electrons are approaching from, we will get overlap with that p orbital. That p orbital has no facial preference. Neither side is more accessible than the other. So we will always get a pi bond formed from overlap of those electrons. Here's another summary slide from your book. For E2, we need a strong base. For E1, look what it says, weak bases work. Remember the parallels between SN2 and SN1. Remember that for SN2, we needed a strong nucleophile. But for SN1, we could get away with a weak nucleophile. If you remember why that was, it was because in SN1, we were dealing with a full positive charge. So we don't need as strong as a base or as strong of a nucleophile to remove the hydrogen because these electrons are very, very attracted to that carbocation already. So we don't need as strong a base in E1 as we do in E2, which parallels SN1 not needing as strong a nucleophile as SN2. Because E1 also involves the leaving group leaving on its own, we need a good ionizing solvent like we did for SN1, but we could use a wide variety of solvents for E2. For E1, because our leaving group again has to leave and we're generating those carbocations, you need to make a stable carbocation. With E2, because we are not making a stable carbocation in either case, we're never making a carbocation, it doesn't matter what the degree of substitution is. But you always need a good leaving group. E1 has first order kinetics, E2 has second order kinetics. That shouldn't be surprising. In both cases, you get the most substituted alkene. Both of these elimination pathways follow Zaitsev's rule. E1 does not require any special geometry, whereas E2 requires coplanar transition state. Rearrangements are common for E1, like they were for SN1. They're impossible for E2, like they were impossible for SN2. A couple more ancillary topics that I want to cover. We've already looked at methyl shifts and hydride shifts, which are illustrated here, where we take for example, a secondary carbocation and move a methyl group over to give us a tertiary carbocation, or we have a secondary carbocation and we move a hydride over to give us a tertiary carbocation. In both cases, we are increasing the stability of the charged species. This tilde methyl and tilde H just is shorthand to say we are doing a methyl shift or a hydride shift. The other type of rearrangement that is possible is something called a ring shift. That's a little bit more tricky to see, but you'll notice what's going on here if you pay attention. Essentially, the ring, this four-membered ring, is opening up. These electrons right here are letting go of the bond, and they are instead grabbing onto the carbon that had the carbocation. So one carbon is losing a bond, the other carbon is gaining a bond. So you still have the positive charge, but what's changing? Two things are changing. We are going from a primary carbocation to a secondary carbocation, which is good, but we are also making the ring bigger. We are expanding the ring from a four-membered ring to a five-membered ring. Remember what we said in the alkanes chapter, that 5 and 6-membered rings give us nearly ideal bond angles. Smaller and larger rings are strained. They have what we call ring strain and angle strain. So opening up a 4-membered ring and reclosing it as a 5-membered ring is a very good process. That will happen very rapidly because the product is so much more stable than where we started. So you can go from a 4-membered ring to a 5-membered ring, or from a 5-membered ring to a 6-membered ring. You could also theoretically shift from a 7-membered ring down to a 6-membered ring. Ideally, you'd always go to a 5 or a 6-membered ring. There's a special kind of elimination called dehydration. Essentially, this is elimination of an alcohol by a strong acid. Here's how it works. Here's an alcohol. It's a secondary alcohol. So this would be potentially following an E1 or an E2 mechanism. But we first, by mixing the alcohol with a strong acid, end up protonating the alcohol. Alcohols are relatively strong bases, Their pKa is about 16. So they're moderately acidic, which means they're moderately basic. So if we put them in the presence of a very strong acid like H2SO4, sulfuric acid, the base will grab an H plus from the acid. So when we protonate that alcohol, we generate water. Remember that water is a good leaving group, HOH, where O is positively charged. Water was on that table of good leaving groups, which means that if we have a base, which we now have the conjugate base of our acid, we could do an elimination. So to regenerate our acid, we're going to take our conjugate base, we're going to grab the adjacent hydrogen, the electrons fall in to make the pi bond, and our leaving group leaves. That gets us our double bond. The reason we call this dehydration is because we have lost water. We lost an OH and an H from our molecule, and we have lost water as our leaving group. It's now floating out separately from our organic product. Also notice that this is acid catalyzed. We consumed the acid in the first step, but then regenerate the acid in the last step. So common acids that will do dehydration are sulfuric acid diluted in water, which is sometimes written in shorthand as H3O plus, because when you mix H2SO4 with water, water gets protonated from the acid. Alternately, HBr is another good acid for doing dehydration. It's nothing other than elimination. Whether it be E1 or E2, the result is the same. It's the same mechanism, it's the same product. The only difference is that we first involve protonating our alcohol from an acid, and then the conjugate base of that acid acts as the base in our elimination process. So here's where we are so far. This is what I call a reaction map. What I'm doing here is I'm in one picture trying to link together all of the reactions that we know. For example, we started with alkanes and we did a free radical halogenation. One thing here, remember when we did free radical halogenation, the reagents were Br2 or Cl2 and light. NBS stands for N-bromosuccinimide, and it is an alternate source of bromine radical when mixed with light. So in the event that you see NBS and light, just remember that it's the same thing functionally. It does the same thing as Br2 and light. So it is a free radical halogenation reagent. So we could take our alkane and do a free radical halogenation, put on our bromine. Now remember that the reason that that's useful is because bromine's a good leaving group, which means that we can do a couple things to it. We could eliminate it using a base and heat. So KOH, very strong base. We do an elimination. There are adjacent hydrogens on either side of this bromine. So we could do an elimination and get our double bond. We could also use a nucleophile and do a substitution. Now I'm also using KOH as my nucleophile. Why am I doing that? Well, remember that hydroxide is a good base. We know that, sodium hydroxide, potassium hydroxide, very classic strong bases. But hydroxide is also a good nucleophile. And I wanted to take this opportunity to clarify that in the event that your base / nucleophile could do elimination or substitution, you can use heat to tilt the scales in favor of elimination. RT means room temperature. So a base nucleophile with heat will favor elimination. A base nucleophile at room temp will favor substitution. So here's our elimination product. It's the alkene. Remember that we could hydrogenate the alkene. H2 and platinum, or H2 and palladium on carbon, will hydrogenate the alkene and turn it into the alkane. We saw that in our hydrogenation slide right here. Alkene, H2 palladium on carbon makes the alkane. Or if we substitute, we now have an alcohol. And remember that we've used alcohols twice already. I just showed you eliminating an alcohol using sulfuric acid. So we could take the alcohol and eliminate it to get back to our double bond. Or in our very first slide today, we used an alcohol as a nucleophile. So we could do a substitution on another cyclohexyl bromide and get an ether as our product. This exact reaction was what we started with at the beginning of the lecture. So this one slide captures everything that we've learned so far about organic reactions: free radical halogenation, elimination, substitution, dehydration, hydrogenation, and nucleophilic substitution again, either with a charged nucleophile like OH minus or a neutral nucleophile like an alcohol, OH. I have a couple practice slides that I would encourage you to take a shot at on your own. We can probably work on them in class as well. Here's a problem. It says refluxing bromomethylcyclopentane in methanol gives a mixture of the following 5 compounds. Propose a mechanism to account for each of these products. So I'm telling you that when you take one reactant and one reagent and we mix them, you get 5 different things, which means that there are 5 different mechanisms occurring here. And I want you to show mechanisms that explain each of these things. Now, if you're observant, 3 of these have double bonds in them. So the 3 products with double bonds must be coming from an elimination mechanism of some sort. And the ones that have an OCH3 on them, this product and this product, have substituted the bromine. So those must involve substitutions. Also notice that we are starting with a 5-membered ring, and in 2 of these products, we end up with a 6-membered ring. If you're observant again, you're thinking, okay, there must be a ring shift going on. And if there's a ring shift going on, that means that it would be a first order mechanism. The double bond must involve an E1, and the substitution must involve an SN1. So give these a shot. It's not necessarily going to be easy. You need to learn the mechanisms, understand how they work. I want you to draw them out, show me step by step how you get from our starting material and the reagent to each one of these products in their own separate mechanism. One other thing that we can do in class is something called synthesis, where we were going to start from, I'm telling you here, butane, and using any number or combination of our reactions, convert butane into this molecule. You can give it a shot. If you're, again, observant, notice what's different from butane. We've got a double bond here. We've got an O-methyl here. So we need to figure out how to put those 2 things on butane using any number of steps. That's the end of lecture 9. Again, this was chapter 6 from Wade, kind of the second half of that. The Stramanis workbook, chapter 14, contains material and practice problems and more exercises from this material.